This is a carbon, double bonded to an oxygen, and it's also single bonded to this OH group. And it turns out that that makes an organic compound, a carboxylic acid, okay? And we'll get into those later. For right now, I just want you to be able to recognize that this little group right here indicates that something is an acid, okay? So I'll just put a little bit of blue highlighting around that so that you'll have it in your notes and that you'll know to do the exact same thing. I'll put little dashed lines here. Okay, and this is your carboxylic acid group. Okay, what we really call that is a carboxy or carboxyl group. Okay, but it's fine to think of it as a carboxylic acid group. Okay, so this is what makes this chemical acidic, and that's going to be present on these other acids that I'll draw, but I'm not going to highlight it there. Okay, but you're just going to know that it's there. So like oleic acid is interesting, right? That's roughly a third of the fatty acids in plant fat. Okay, like say olive oil. Then there's linoleic acid, and so linoleic acid looks like this, and it's also got 18 carbons. So 1 carbon, 2, 4, 6, 8, 9, double bond, same place, 10, 11, 12, and then you've got another double bond right there, and you go 13, you go 14, 16, 18. Okay, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 carbons. And let's count with me, guys, on the carbons here. Okay, we're going to go from this guy. Ready, set, go. 1, 6, 9, 10. Okay, and so that's how you make sure that your skeletal structure is right? Like I'm a fully trained chemist. I could go work for a chemistry company tomorrow and I would fit right in with the other chemists. And I have to make sure that I'm accounting for all of my atoms, right, when I draw out my skeletal structure. So you'll use the same practice, okay, and you'll feel good about that because when you're counting and you're being careful, you're being a good chemist. So this guy's called linoleic acid. And here's something that's really interesting, okay, and I can capitalize that. So this guy is polyunsaturated. Right? This guy is called monounsaturated. And the question is why? The answer is that when you have a double bond here, you've actually got 2 fewer hydrogens there than you normally would. So like here and here, right, you've got CH2 and CH2. But here, on this carbon, you've got 1 carbon-carbon bond. You've got 2 more carbon-carbon bonds. So this carbon's bonded 1, 2, 3 times the other carbons. That means it can only fit 1 more hydrogen there. This carbon can only fit 1 more hydrogen there. So these aren't CH2s, these are CH1s, okay? We may get into that further later. You may only see that once in this lecture, and it may live in your notes, and it may live in your video, and you may not think about it again until you get to AP Chem, and that would be okay. But I want you to understand, monounsaturated, 1 double bond, which takes away 2 hydrogens, okay, 2 hydrogen atoms. Linoleic acid, polyunsaturated. Poly means many, just means more than 1. Okay, you could also call it diunsaturated if you want to, which means 2 unsaturations, but you've got 2 double bonds. Those take away a total of 4 hydrogen atoms, okay? And these are natural unsaturated fats. These are totally fine for you to eat, okay? You can totally eat these and you're in good shape. The last one is palmitic acid, and you've got 1, 2, and you've got OH, okay? And palmitic acid is C16 with no double bonds. So here's how I'll draw this guy. I'll go 2, 4, 6, 8, 10, 12, 14, 16. I'm done. Palmitic acid. Let's double check. 2, 4, 6, 8, 10, 12, 14, 16. Yep. Palmitic acid. Okay. So what in the world happens here? Why did I just draw this glycerol backbone, and why did I draw these things? It turns out that when an olive oil molecule is made, and if you have some olive oil, like olive oil itself, many of the molecules inside might actually, or will actually consist of like this guy plus this guy plus this guy, all on the same glycerol backbone. So what we do chemically is, or as chemists, we draw a little plus sign, and we say this thing plus these things makes another thing, right? So we draw our little reaction arrow, and we get this bad boy right here. And I'm going to draw it a little smaller, okay, because I'm running out of space on the board. But I'm going to go like this, and I go O, carbon, double bond oxygen, and then I go just like I did before, so 2, like that, and then I go and last one, who's eating chips?
No.
Those weren't chips?
No.
What was that crunch?
No crunch.
I heard a crunch. Okay. 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. Palmitic acid. Okay. And then, so, for those of us keeping score, okay, the crazy part is that when you bond them like this, you actually lose an H, an O, and an H, okay? So, like, if you look really closely, you've got, like, this oxygen, or this oxygen actually, coming in here, and it kicks out all 3 of these. Okay? These guys get like added together. And so what you actually do is you create this, and we got to keep track of all of our chemicals because we're chemists, right? Plus 3 H2O molecules. Okay? And so this guy right here is called a dehydration synthesis. Okay? That's what this thing is. This process, this reaction arrow, represents a dehydration synthesis. Okay? We're making our triglyceride. This thing over here is called a triglyceride. Okay? This is a triglyceride. Why? Because you've got 1, 2, 3 fatty acids on a single backbone that we call what? Glycerol, right? Tri-3-glycerol, okay? Triglyceride, that's what we have going on, okay? Triglycerides, triglyceride, okay? So you've got like 3 fatty acids, okay, glyceride, right? You've got your glycerol backbone, okay? And that is a fat. So, olive oil looks roughly like that, okay? That's a good representation of the different molecules that are in olive oil, okay? So when you eat some olive oil, you're eating triglycerides. You're not eating glycerol for sure, and you're not eating individual fatty acids. You're actually eating them packaged up like this, okay? Animal fat also exists in triglyceride form, but its fatty acid composition is different. Which fatty acids those are, and why animal fat is solid at room temperature, while plant fat is liquid at room temperature, those questions will wait for next time.